Good. I've given a very grandiose topic, and I want to lower the pressure for myself by saying this is not my inaugural lecture, and I'm actually going to give quite an informal talk about some really hot off the press results that I'm very interested in right now. Because I'm new here, I'm literally been here for a month, I wanted to just briefly introduce myself. Yes, I'm the new professor of astrophysics, 1909. My office is H51. And if you see my door open, please come and talk to me, or come and talk to me at coffee or tea. I'm very, very interested in talking to you and finding out what you're doing, and maybe we can even work together. I've got a very broad span of research interests. I work in essentially connecting fundamental physics with astronomical data across the wavelength spectrum, and increasingly also multi-messenger data, for example, with gravitational waves. And I'm also engaged in motivating and actually designing astroparticle physics experiments as well. And I have a lot of very strong methodological interests, including hierarchical Bayesian modeling and advanced machine learning techniques. Most of my talk will concentrate on the machine learning part today. And currently, I'm basically spending my time on 4 things. The first is an ERC advanced grant project I'm leading, which is basically about developing new methodologies to tackle some of the really crucial challenges we face in the coming data set from the Vera Rubin Observatory, and also developing new cosmological probes of the nonlinear universe, particularly with that data set, with a strong focus on explainable AI methods. So most of my talk will be on a project that we're doing within that, grant project. And I'm also working on extracting fundamental physics from populations of compact object mergers, like we can expect in the coming decade from the LIGO A+ era, which is going to be very excitingly concurrent with the Rubin Observatory's LSST survey, so enabling very synergistic science there. I'm very much interested in testing the axion dark matter hypothesis, both from cosmological data and in astrophysical settings, and also in the laboratory. And in a leap quite outside the mainstream, I'm also working at the intersection of cosmology and quantum technologies to try to emulate theories of the early universe within a condensed matter system. That's a collaboration I have ongoing with Zoran Hadzibabich group in physics. So that's a little bit about me. And so moving on to some science. So we live in very exciting times. So just in the last year, we have had pulsar timing arrays announced the detection of a stochastic gravitational wave background. IceCube announced the detection of neutrino flux from the Milky Way. And Euclid has successfully launched, is talking to the Earth, and it is currently undergoing science verification. So as we speak, new windows are opening on the universe. So we currently live in a very exciting era of surveys. So surveys are attempts to take representative samples of the universe from which you can hopefully make global conclusions about the origin and evolution of the universe and the structure within it. And we have for a long time been surveying the sky across the electromagnetic spectrum, but increasingly we are now able to do this in a multi-messenger fashion with the detection of gravitational waves and now neutrinos. And so that's the forward look on the field, but also taking a step back, just to reflect on the highlights of the last couple of decades of research in cosmology. We've determined the parameter of a basic cosmological model. We've measured the age and the composition of the universe. We've found strong evidence, but not yet a smoking gun, for the quantum origin of primordial structure. And measurements of the cosmic microwave background and type 1a supernovae are cornerstones of that achievement. But in my view now and in the future, progress will come only through multiple complementary probes, providing a synergistic complementary view of the evolution of the universe. And we have to say that major theoretical questions remain unanswered. what is dark matter, what is dark energy. These are questions that were asked when I was an undergraduate. We're still asking them, and we don't know the answers yet. So I see a lot of young faces in the audience. There are lots of puzzles for you to solve. So as I said, quite a lot of information we've learned about the universe has come from studying the cosmic microwave background. The initial conditions of the universe are very well described by linear theory and Gaussian statistics. So they are very amenable to modeling the observations accurately and being able to back out scientific conclusions very robustly. But in the coming era, we have to deal with data from the very evolved, very nonlinear universe. And extracting scientific conclusions robustly from those kinds of data is much more challenging. And so in this era, we have to, I think, re-ask the question of how should we compare theory with data. Cosmological interpretation is increasingly reliant on evaluating computationally costly, non-linear models with many, many parameters. There are different people, both in Cambridge and many people around the world, bringing different approaches to that particular problem. But I'm going to talk about whether machine learning can play a role here. And in particular, I'm going to talk about three things. One is emulation, which is just a complicated word for saying you take a computation and you make it fast, but do it accurately. So a machine learning acceleration of what's called forward modeling of observations. The second is simulation-based inference. This is high-dimensional cosmological inference with machine-accelerated parts where you don't write down an explicit likelihood. You don't know the explicit likelihood, but by doing forward simulations, you can work out the sampling distribution of the data under the model that you want to test, and you can directly essentially compare mock observations with the actual data and work out what that implies for the model. I did try to time this talk this morning, and I had really wanted to talk about explainable AI as well, but I had to cut that part. So, but I will say at the end a few words about explainable AI, which I think is a very, very powerful tool that we can do to automate scientific discovery, especially about emergent properties of the universe that arise during cosmological structure formation. So let's get to the observational frontier with galaxy surveys. I picked one problem that I'm working on related to trying to do this comparison with data and theory in a setting that has previously been extremely challenging. And so when it comes to galaxy surveys, there are two complementary types. There are spectroscopic surveys where you get a high signal-to-noise spectrum per galaxy, so you will get an accurate redshift about it and also many other information about that galaxy. But because taking spectra is expensive, you only get a lower space density of galaxies that you can sample like that, and also you need to reach a certain signal to noise, so actually you can't really survey the universe that deeply with that method. Photometric surveys basically apply broadband observations to galaxies, so you can go much deeper and you can get much more space density of galaxies in your sample, but unfortunately, the information about each galaxy, and in particular its redshift, is not determined as accurately. So the survey that's going to do this latter type of observation, photometric survey, the one that's on steroids, is called the Vera C. Rubin Observatory's Legacy Survey of Space and Time. So this is the survey I've been spending the past few years preparing for, and I'm very, very excited about it. It is a wide survey. It's half the sky. It's very deep, up to 27 magnitude. And really interestingly, it will survey the universe that's not been done before at this scale, which is a sort of complementarity between static observations, static deep observations, and fast. It literally will survey the southern sky roughly every 3 days and do that for 10 whole years. So thereby, it will make our first movie of the universe, and that mode of static cross-transient is opening up a very exciting discovery space, and we will probably find things that we have never seen before. Beginning in January 2025, so LSST will start to send us a deluge of data. I personally feel quite scared about this because I don't feel that we are actually ready to handle that data, but hopefully what I'm going to present is showing us one way forward to do that. So this survey will expand space-time volume a factor of 1,000 over existing surveys, and it will carry out 4 scientific missions at the same time, very detailed investigations of dark matter and dark energy, an inventory of the solar system, this movie of the universe I was telling you about, and also a very detailed map of the Milky Way, which will incidentally enable very detailed tests of the nature of dark matter as well. So it's 37 billion objects in space and time, 30 trillion measurements, and it's 60 petabytes of raw data, 250 petabytes of processed data, and 20 terabytes of data per night. So just to translate that into something it's easier to appreciate as a human, that's 10 million alerts of something changing on the sky every night. And so there's an enormous needle in haystack exercise if you want to, for example, dig out very rare sources out of that. So it's been very exciting to see this survey go from architectural, artistic drawings to a real thing. I was very lucky to see the LSST camera this summer in the laboratory. They're putting the finishing touches on that. It's the biggest digital camera ever built. It's a beast. It's the size of a car. And this is a very exciting time for people that have cared about this survey for about a decade. So when we are faced with data of that volume, it's really big data, both in its volume, but also in the rate that it's arriving and also its complexity. We are going to need new methodological advances in order to compare our theories with that data. And that's because even though we have been in this era of precision cosmology, it's getting smaller and smaller error bars on the parameters we care about. In the LSST era, or even now really, we are not limited by statistics. We are limited by systematic errors, and systematic errors that particularly depend on unknown astrophysics. So there are known unknowns and unknown unknowns. They can bias our tiny error bars away from the right answer. So we need to enable the era of accurate cosmology. And just to take one example, looking at LSST and dark energy science. So this plot basically shows 2 dark energy parameters that signify whether it's evolving with time. If you're a cosmological constant, you will be living in the middle there. And after 1 year of the LSST survey, you will have combined a bunch of cosmological probes to get a tiny error bar. And after 10 years, it will be even tinier error bars. The accuracy requirements involved in making those measurements are really stringent and really scary. And in particular, we have to now face the fact that the survey is a photometric survey. So photometric catalogs, like LSST's billion galaxy catalog, requires redshift estimation. So if you have nice spectra per galaxy, you can work out its redshift pretty accurately. But instead, this is the filter set of the Sloan Digital Sky Survey. LSST will have 6 filters. You basically get a poor man's estimation of the colors that characterize the spectral energy distribution of the galaxy, and you have to take that lossy compression of the data and infer the redshift accurately. So here's an example showing an animation of a galaxy spectrum that's going to be now redshifted through these filters. And down here, you will see how the redshift correlates with fluxes in various bands. And so you can see there's lots of degeneracies among these colors and the redshifts, and you have to be able to accurately back out that lossy compression. This is particularly of concern for what is potentially the most precise probe that LSST will have, which is cosmic shear or weak lensing. So cosmic shear is the effect of light traveling across cosmic structures to us, being very slightly deflected by those cosmic structures. And this is a very, very exaggerated cartoon. It slightly changes the positions and the shapes of the galaxies. You can probably very intuitively work out that if you had misestimated where the galaxies really were, what redshift they were at, you are going to misestimate the amount of deflection that they have along the line of sight, and therefore you're going to make biased, wrong inferences about the amount of growth of structure in the universe, for example, and therefore bias your cosmology. So to be able to do this redshift estimation at the sub% precision necessary for LSST is a very challenging task. So far, we have been relying on spectroscopic training sets or spectroscopic recalibration in order to work out, given the redshift distribution of photometric redshifts in a given bin of redshift. Once you estimate that, you have to recalibrate to work out what is the actual underlying redshift distribution. And if you get those things wrong, if they're biased in their mean with respect to each other, you're going to literally see this bias that I was describing. And unfortunately, this method, I don't think is going to scale for LSST, and I think it's probably problematic even now for the current stage 3 surveys. So spectroscopic samples are typically not representative of photometric catalogs. They have brighter flux limits, and of course the galaxy population evolves over cosmic time, so they may not even be representative of deep samples like what we're going to get from LSST. They are typically heterogeneous, and they contain difficult to model selection effects. It's not like saying, oh, here's a survey, we targeted everything brighter than a certain flux cut in a particular band. They have complicated selection effects. And this can introduce biases which are difficult to mitigate at the required precision. This is a simulation study from the Dark Energy Survey. And basically what I'm saying is that if you think that your underlying redshift distributions are these colored ones, and the actual ones are these dashed curves, then those shifts will translate into cosmological biases. So this is a problem that we've been thinking about for some time. And it's an approach that actually we initially thought about in 2016 with Boris Leisted and Daniel Mortlock. And that was to actually try to solve the problem by making it even harder. So the key idea was to simultaneously learn the redshift distribution and the full evolution of the full joint distribution of galaxy properties over cosmic time. So first, this is basically saying we want to learn the joint distribution of galaxy properties in the universe. For example, astrophysical ingredients such as mass, star formation history, dust, gas, metallicity, impact of AGN. So if you could do that, you could forward model your data set, and that allows you to predict spectra and broadband colors of galaxy samples through something called stellar population synthesis, which is quite a standard technique in astronomy. So if you haven't heard about it, stellar population synthesis in principle is quite simple. You basically add up the spectral energy distributions for all the stars in each individual galaxy at their ages and metallicities. You add the impact of dust attenuation and emission on the SED. You add nebula emission and gas physics. So from a compositional perspective, that is quite simple. But let me just say, each of these areas is like a whole subfield of astrophysics in itself. Actually, the physics that goes into modeling these elements is quite challenging. In the work I'm going to present, we are not going to address these elements. We take the state of the art, which is the FSPS, the flexible SPS models that were put forward by Charlie Conroy and others. But as our work progresses, I think we can also have impact on better modeling of these components as well. But I'll come to that in a minute. So, what's the big deal? Why is it so hard? A forward model of the data set will involve, as I said, a model of the population which models the full joint distribution of all of those astrophysical ingredients. A model of the data. So you have to take your predictions from the galaxy evolution model and make that into the data by adding the right levels of noise and adding the 0 points of the data and so on. And then on top of that, you have to understand your selection. How did a galaxy make it into your sample? What are the characteristics it must have to make it into your sample? So these are quite challenging things to model. And that's because of these 4 bullet points. Computing these SPS models is expensive. That turned out to be the easiest thing to solve, so I'll just flag that now. The hardest thing was that there is no good parametric model for the whole galaxy population. And that we only managed to solve in the last 2 years because of methods that only became available in the last 2 years. And then once we did this one, we were able to solve these 2 as well. So individual galaxy posteriors, if you were trying to do inference in the standard hierarchical Bayesian setting, where you sample the source parameters and then you sample the hierarchical parameters, that is like my favorite technique. But I don't know if some of you were in the talk I gave here in March at the Rubin LSST meeting that was organized by Suhail. But at that time, I was still trying to make hierarchical Bayesian modeling work. And we gave up on it because it's not scalable. And then finally, selection effects means that inferring the population model is intractable anyway. So these were the problems we faced. And so we approached this with an amazing team. These are members of my ERC team and also friends. Justin Alsing, who's a machine learning genius, Boris Leisted, who's analyzed galaxy surveys, treating systematics in a very principled way, Sinan Degger, who has just moved with me here. Sinan, are you here? There you go, he's there. And I'm going to leave some of the stuff we're doing for him to talk about, so please invite him to give a talk at some point. And also Stephen Thorpe, who is an alum of the Institute, who is now working with me in Stockholm. And he used to be part of KZ Mandel's group, and now he's also working with us on these topics. So anyway, the 4 bullet points, how did we crack them? The first one was the easiest one to crack. We already did that in 2020. And that was basically using emulation for SPS models. So actually, SPS models are relatively fast to evaluate, about a second per model evaluation. But the problem is that use cases require very large numbers of model evaluations. So, for example, a stage 4 catalog simulation is about 10 to the 10 SPS evaluations. Our collaborator, Joel Leja, basically, his analysis, this is a seminal analysis of 60,000 galaxies from the 3D HST survey under a 14-parameter SPS model. That cost 1.5 million CPU hours, just 60,000 galaxies. So, the Cosmos catalog I'm going to show you is hundreds of thousands of galaxies. Kids Viking, which we're about to analyze, is millions. and LSS is billions. So that's not going to scale. However, you can generate training sets of 10 to the 5 or 10 to the 6, and that enables accurate neural network emulators. Our emulator is called Speculator. This emulates SEDs. We have an emulator called Fortulator that actually emulates broadband colors as well. This is actually a very flexible framework which has also been adapted for other emulation tasks in cosmology. For example, it is the underlying engine of the so-called Cosmo Power that emulates CMB spectra and matter power spectra. So this might actually work out of the box for your emulation problem. So have a look at it. But anyway, that was the way we solved it. And this was a case study we presented in that paper, which was a case study for the DESI Bright Galaxy Survey SEDs. The accuracy was better than percent precision over a 8-parameter FSPS model for more than 99% of the SEDs. And basically, it speeded up doing computations on a CPU with FSPS by a factor of 10 to the 5. So the other thing that a neural network emulator can give you is that you can make use of gradients. So if you want to do inference under these models, for example, using Hamiltonian Monte Carlo, that directly enables doing that. Or if you want to do directly machine learning optimization with gradient descent, as I'll show next, that will also enable this thing. Okay, so that was the first one ticked off. And then we struggled mightily for 2 years to do this one. There's no good parametric model for the whole galaxy population. I showed you a bullet list of the basic astrophysical ingredients that need to go into a stellar population synthesis model. And so, parts of those models are still parametric. People take some combination of astrophysical ingredients, ignoring all the others, and then somehow they can factorize the model and parameterize them. But even then, people were starting to use things like normalizing flows to describe other aspects of the model already. So we decided to take this and go all the way to a machine learning model. Machine learning models can accurately describe very complicated distributions. I'm not going to turn this into a talk about machine learning technobabble, so I'll try to express this in a kind of understandable way. It's basically a flexible neuro probability density model for aficionados in the room. So these are things like normalizing flows. So what we ended up using are diffusion models because they're much more stable to train. And so this is like a flexible mesh in a very high dimensional space, like in this case, 15 or 16 dimensions. And this mesh is continuously deformable, preserving probability. And so you can use that to describe any complicated function. So for example, we can use it to describe the population prior, the data model, and selection. So what you actually do is you learn a ODE, or a stochastic differential equation, that transforms from a very simple distribution, like a unit normal, into the joint distribution of galaxy properties over cosmic time. So what I'm going to show you now is literally hot off the press, results that are about a month old. And I want to try to explain this with a very, very nice toy model that Justin Elsing set up that illustrates how this works. And I think this idea is actually quite transferable to so many areas of astrophysics. So the basic idea might be useful beyond this problem. Pardon me. So basically, you take some base samples from a very simple distribution. And then the first thing you want to do, I'm going to show the animation in a second. You draw from the population model. And then that gives you a realization of a population of galaxies. But it's still not data. You have to then compute observables So this will be the astrophysical ingredients. Then you have your emulator that takes that and turns it into observables like SEDs or colors. And then you do the same on this side to add noise or perform your data model, and you can make realizations of the data. So basically, it's a quite intuitive idea. You simulate mock data by drawing from a complicated prior, and then you tune the parameters of the model till the mock data resembles the real data as well as possible. And to do that, you need to be able to take gradients through the simulator. So that was helped by the fact that we have a neural network emulator in that step. So let me show you the animation of how that works. So you can see the simple density is transformed through this bijector into a complicated population model. And then you turn this into observables by running your neural network emulator. And then you add noise, and then that gives you a realization of the data. So you've done the forward modeling part, and we find this works remarkably well. So then you have the actual data, right? So the actual data in this case will be in here, the blue. So on top of adding noise, adding the data model, you have to also apply selection. So this is the second thing that is really cool about this method. If you cannot express selection in a simple way or in a parametric way, you just have to be able to simulate it. It can be as complicated as it needs. And so then you have realizations of your data. And now you want to take this very high dimensional point cloud and be able to compare it to the data directly. And in this example, so we do something called minimizing the optimal transport loss here. But we found that the loss function can be as simple summaries of the credible intervals in color space, for example, and it still works well. So essentially, you are optimizing as this loss descends so that your population prior, which is living over here, makes realizations that matches the data. So that's the last one solved. And effectively, it solves these two things for you, because the selection effects can be as intractable parametrically as they want, but you can still forward simulate them, and they can be as complicated as they need to be, and you never have to sample individual galaxy posteriors. You're directly comparing the population with the full data set. So that was very exciting. And so once we got that method working, we wanted to apply it to the Cosmos 2020 catalog. This is the deepest catalog currently available of a substantial size. It's hundreds of thousands of galaxies. And it's not spectra, but it's got both broadband data and narrowband data on this very deep and high fidelity observations. So the photometric data we use was this Cosmos 2020 multi-wavelength farmer catalog. The population model we used was based on a state-of-the-art SPS model prior called Prospector Alpha, but we call it Prospector Alpha Plus because we did some refinements to the way that metallicity evolution is treated. And then we have emulators of both the flux and the emission lines because this has narrow bands as well. And the data model involved optimization of 0 points per band and broadband and emission line hyperparameters. So then we do this optimization, and this is the quality of the fits that we get in color space. These are just some representative colors. As far as we know, this is the first time the full joint density of galaxy properties over cosmic time has been estimated from a large galaxy catalog. You can probably have your eyes drawn by this one, which doesn't look like it's such a good fit. But actually, that's an issue with the data. It's known that the IRAC1 colors in these Cosmos catalog are somewhat misestimated. But because of the way we have treated the data model, our fits are not being particularly dragged by that. But those fits look good, so we were encouraged, and we moved on to the thing that I personally care about, which is, can we get some redshifts out that we can then use for cosmology? So this is the quality of our map estimates under this PopCosmos population model versus full MCMC inference of the posterior of each individual galaxy in the catalog. I started by saying, oh, well, that's going to be intractable. But we have this very clever guy, Stephen Thorpe, working with us, who managed to get affine samplers working on GPUs. So he managed to crank through the Cosmos catalog. I still don't think it's going to be scalable for any big catalog, but it allows us to show that map estimates and the full uncertainties on the map estimates are very compatible. Basically, they should lie on this x equals y line. There are some things we're still interrogating about this. For example, this tiny fluctuation to lower values at redshift of 3.5. But these are details that we will be refining. And then the redshift distributions. So this is the redshift distribution of the Cosmos 2020 catalog under our PopCosmos population. And it's compared with estimated, map estimated results from the so-called Lefebvre method, which is a photo Z method that is fairly state-of-the-art. So, you know, yes, there are big spikes in this distribution, but it looks reasonably compatible. So we are going to pursue this approach for doing redshift estimation with weak lensing surveys. But there's more, because we fitted the full population of galaxies and their evolution and their astrophysics. We have results on the conditional distributions of the star forming sequence. And so these plots are basically showing stellar mass versus star formation rate over cosmic time. The gray shows where the selection applies. So the catalog we used has data above the gray band, but it also shows how these various distributions extrapolate outside where we fitted. And there's results on the evolution of metallicity. So here we have gas metallicity on this side, stellar metallicity on this side as a function of stellar mass. There are interesting trends here, both with redshift and with stellar mass. And then there is information about dust and how dust parameters vary with stellar mass, and how diffuse dust attenuation is correlated with the dust law index. I'm hoping that you will ask Sinan to talk about these things later on, hopefully this year. So I'm not going to steal his thunder, but we are very excited about how these kinds of approaches can go back to shed light on the interface between cosmology and galaxy evolution. So now our next steps are to take this calibrated PopCosmos population model to conduct the weak lensing analysis of the kids' Viking catalog. We are currently learning the complicated selection function of the kids' Viking catalog within a ML classifier. It's very complicated. It's not like saying, oh, it's a cut with this signal to noise in this band. The selection function depends on the image quality and the quality with which shapes can be measured and extracted from the images. So it cannot be parameterized. So this approach will just take that in its stride. And the redshift distributions will be directly predicted. We're not going to fit them again by our PopCosmos calibrated model. And it's really, really cool because KIDS is a bit brighter than Cosmos 2020. And even with LSST, we might be able to use the Cosmos calibrated model because the depths are actually quite compatible. So then another question is, we're not going to have spectra to validate these methods. If you were around in my talk in March, I showed our preliminary analysis showing that we could predict the redshift distributions of spectroscopic catalogs extremely well with a much simpler population prior than this. But those are very bright compared to the depths that we will be needing to analyze in the Rubin era, or even now with kids Viking. So we are developing what's called Bayesian cross-validation or posterior predictive checking in color and flux space. And so these two works are being led by Otto Loureiro and Stephen Thorpe. And hopefully I can come back someday and tell you about how we fared. So this is a very exciting time for us because the kids team have been superb. They're very open with their data. They have given us everything. They've answered all our questions. This is the way that scientific collaboration should work. And so we are doing an independent analysis of their data with a completely different way of doing the redshifts, which has never been done before, I think. The current existing methods all use very similar methodologies based on spectroscopic recalibration. So either we will confirm their methods, or else we might find that, for example, we get very different results on the sigma 8 tension from what the collaboration found. So watch this space. In the last couple of minutes, because I don't think I had actually time to talk about explainable AI, I just wanted to give some broad perspectives on this. So what are machine learning models good at that specialize it to astronomy? I hope I've convinced you that they can provide fast, flexible models for mapping between complex, very high-dimensional data sets, for example, for classification, and also for accurately speeding up forward modeling calculations for data emulation. And there are many applications where physical models are simply not available or tractable, like anomaly detection or automated discovery in very large data sets. Let's now enumerate characteristics of good physical models. Hopefully, they follow from explicitly enumerable assumptions and physical principles. Hopefully, it leads to a mathematical model that can be solved either analytically or numerically, and then lead to predictions either deterministically or probabilistically. They should be explainable. They should be rooted in cause-effect relationships, grounded in domain knowledge. They should hopefully generalize beyond the initial domain in which they were fit to explain a wider range of phenomena. And they should compress information. They should explain a wide range of phenomena from a minimal set of ingredients. This is some encapsulation of the concept of Occam's razor. And the domain of validity, hopefully, can be quantified explicitly so that you don't accidentally step outside that and use it in a domain that should not be used. Effective field theory is a very good example of that. So it would be good if machine learning models acquired some of the characteristics of good physical models. And in my view, this requires two things, which are two related concepts, which are not the same but related to each other. One is interpretability. You must be able to, provide an account for why a machine learning system reaches a particular decision or prediction. And the second is explainability, which is the ability to map that account onto the existing body of knowledge in that research domain. And this is currently very challenging because of the black box nature of machine learning architectures, in particular deep learning. You see people falling over themselves trying to explain how ChatGPT works. We don't actually understand how some of these methods work, and therefore we don't know when they might fail and under what conditions they will provide reliable answers. So it must be said, though, that many physical models only satisfy my list of desiderata only partially. For example, systems exhibiting chaos, or systems that have emergent phenomena occurring inside them. And in my view, understanding emergent phenomena in cosmology is really critical to making progress in understanding the nonlinear universe and being able to actually extract information from it reliably. This is the so-called more is different concept, which is a title of a famous paper by Philip Anderson. When you put more ingredients together, the behavior of the system becomes very different from the individual ingredients that you put in. So can we reliably access the rich information in the cosmic web? Can we understand what I call mesoscale phenomena in structure formation? How do universal phenomena emerge? And can machine learning then play a role in building accurate mesoscale models of complex phenomena? Just to make it a bit more specific, here's a list of phenomena that I personally am very excited about and investigating with these approaches. So emergent phenomena in halo formation, halo bias, so that's the clustering of halos relative to the matter density, the halo mass function, long known to be universal, sources of non-universality not yet understood. So that's the abundance of halos as a function of mass. The halo density profile, the distribution of matter within the halo, long known to be universal. After 20 years of investigation, we still don't really understand what establishes universality. So understanding these phenomena are critical, in my view, for accurate cosmology beyond linear theory. And sadly, I tend to cram a lot into my talks. I did cut this because I don't want to keep you here. But we have been developing frameworks for knowledge extraction through AI that addresses some of those questions. And I'll very briefly discuss the conceptual framework that we're using. We take raw data, like the 3D density field, we feed it through a funnel into an information bottleneck. So you're compressing the data. If you're familiar with variational autoencoders, it's a similar idea to that. So in the funnel, you have captured information in a compressed form. Usually what you do is to expand that funnel out and reproduce your data. But that's not what we're doing. We are guiding the training of the network so that it learns to predict in a halo property of interest, like the halo density profile or the halo mass function. So basically, it takes the raw information you give it, and it encapsulates within this compressed model the information that is needed to make that prediction. And then we use techniques from information theory called mutual information to interrogate the compressed model, the latent space that is captured in the information bottleneck. So we've written some interesting papers along these lines, led by a fantastic former student, Louisa Lucy Smith, and other collaborators. We're also actually taking these same ideas and applying them in cognitive neuroscience, which seems to have similar complex data and similar open questions about emergent phenomena as cosmologists do. So I'm very happy to come back and give a more technical talk about these kinds of topics in some other venue, if you're interested. I'm going to wrap up now by saying that there are 4 interconnected pillars for understanding the physics of the universe. The 2 I have talked about here is data. Cosmology is data-driven now. It will arguably be so into the 2020s and possibly beyond. Modeling has become really crucial to interpreting that data scientifically because interpretation relies on accurate modeling, and that's increasingly heavily dependent on both high-performance computing and, as I showed you, hopefully, on very advanced machine learning techniques. So that's what I focused on. But let me just also say that on either side of these two pillars, there's instrumentation. Our understanding of the universe is being driven by technological advances, and that has been so since 1990s, and it will continue to be so in the future. And I think all of these three pillars are working very well and underway. The one I'm worried about is theory. The current understanding of the physics of the universe is empirical. Deeper physical understanding can only come through theoretical breakthroughs. And this is an area of astrophysics and cosmology, which, particularly in cosmology, which seems a bit stuck. There were lots and lots of theoretical ideas when I was an undergraduate, or even when I was a PhD student. Many of those theories have been killed. Other theories make actually interesting predictions for explicit phenomena that you should go and observe. People have looked for those. We haven't found any smoking guns. So, I think that there's a lot of open space there for novel ideas that especially young people in the room might want to pursue and think in a different way from previous generations. So with that message, I'm going to end my talk. Thank you very much.